In the next couple of videos, we're going to be taking a look at an example. So what we want to do is we want to find the voltage gain A sub V of a common emitter circuit without and with an emitter resistor. And so in this first video, we're going to look at part A of this example, which is going to be to find that small signal voltage gain for this circuit shown below, where we have beta equals 120, VBE on equals 0.7 volts, and VA equals infinity. And so a quick note we've mentioned before, but of course when we see this VA equals infinity, what this tells us is that we're going to be neglecting our early effect. So neglect early effect, or in other words, our small signal output resistance of our transistor is going to be infinity. So you might see that presented in any of those three ways. So same circuit we've looked at a couple videos back. The only difference is now we have values for our resistors as well as for our DC source VCC. So note right now we're considering the case of no emitter resistor. Now the first step in doing this is we would need to do our DC analysis. And the reason we need to do that DC analysis is to determine what our small signal hybrid pi parameters are. So we need to figure out our R pi value and our GM value. In other words, we need to find the Q point. And so I'm not going to go through that in this video. That is shown in the notes as practice. So if you want to look at page 418 in the notes, you can see how that analysis is done. What we get from that DC analysis ultimately is a value for our ICQ. So we get that our ICQ is 0.944 milliamps. So with that ICQ value, we can now find our R pi and our GM. So our R pi, remember, is VT times beta over ICQ. So if we plug in our values, let's say we assume room temperature, so we have about 26 millivolts for our thermal voltage, VT. Our beta was given as 120 in the problem statement, and we have our 0.944 milliamps for our collector current. So plugging that in, we get approximately 3.305 k ohms for our diffusion resistance R pi. So we also need our GM, our small signal transconductance, and that's equal to ICQ over VT. Again, we're going to assume that this is approximately room temperature, so we have our 0.944 milliamps divided by our 0.026 volts, which gives us approximately 36.308 milliamps per volt. Okay, so now that we have these small signal hybrid pi parameters, we're ready to plug into that small signal voltage gain equation that we had before. So as you recall, we had already analyzed this circuit and we had a small signal voltage gain equation. The only difference is now, of course, as we said above, we have this R naught is equal to infinity. And so if you want to review that equation in the notes, that's on page 4-15. But what it's going to look like is now we have our AV is equal to negative beta, and instead of R naught in parallel with RC, we just have RC. And we have that's divided by R pi multiplied by Ri divided by Ri plus Rs. Okay, so the last thing we need to figure out then is what is that Ri value. So our Ri value, so let me just move this down and we can calculate it right above here and still use that. So our Ri, so that's capital I, we had defined as being R1 parallel R2 parallel R pi. And again, I'm not necessarily showing where these equations come from. We did that previously. Now I'm just sort of plugging in our values. So if we use that, and again, we have our R1 and R2 given in the circuit now, as well as our R pi value, which we just calculated here. So the parallel combination of all of those is going to give us approximately 3.126 k ohms. And so we can kind of expect that because we see R1 and R2 are so much bigger than R pi that R pi is going to be dominating that parallel combination. So it's just going to be a little less than the smallest one in parallel. So now we have all our values and we're ready to plug into this expression here. So we have our beta, which is 120, our RC, which is 5.6 k ohms, we have our R pi, which is 3.305 k ohms. So of course the k ohms are going to cancel out. And then same thing in this ratio if we use k ohms and k ohms. So we have our 3.126 k ohms for our Ri, 3.126 again, and then 0.5 k ohms for our Rs. So we want to make sure we put that in k ohms. Again, oftentimes that Rs value is going to be small, so if it's given in ohms, you want to make sure you have the same units when you plug it in here, same units as the Ri. Okay, so if we evaluate that, we then find that our small signal voltage gain is approximately negative 175.286. So that would be our final answer. What we're going to see in the next video when we look at adding that emitter resistor is that this gain is going to decrease pretty significantly. But before we look at that, let's consider how much this gain is going to be changing as our beta value is changing. So let's say we have a beta value that changes by plus or minus 50%. So it's starting at 120 here, and then for some reason, maybe we have a temperature change or maybe just process variation. We're switching between transistors, so we have multiple circuits using the same type of transistor, but of course different transistors. So maybe because of variation in production, one has plus 50% beta, one has minus 50% beta. For whatever reason, we have these differences in beta. So what's that going to do to our voltage gain? Well, as we just saw for this sort of 120 case, we have about negative 175.3. And so if we were to decrease beta by 50%, it turns out that our AV is also going to decrease by 50%. Same thing if we increase our beta by 50%, our AV is going to increase by 50%. So we see a plus or minus 50% change in beta. So plus or minus 50% in beta is corresponding to a plus or minus 50% in AV. And so obviously that's not something we want. So that is far from ideal. So going back to sort of our adding the emitter resistor, which we're going to do in the next video, it's going to decrease our gain, yes, but we're going to see a lot less variation as our beta is changing. One other thing to note too is that, of course, as we're changing this beta value, so any change in our beta is also going to result in change in our Q point, so change in our ICQ, and consequently change in our small signal transconductance G sub m.